In this module, we will explore the concept of residual analysis for generalized linear models. You have already learned about the concept of a residual for a linear model. So once we have fitted a linear model using, say, the technique of least squares, we would like to know how adequate the model fitted is. There are several ways to do this. One would be to look at a summary criterion measure, such as R-square or adjusted R-square. The other would be a more intuitive and perhaps subjective approach based on the residuals. So you know that it is possible to plot residuals against fitted values, against covariates, and so on, to explore whether we have included all the predictors, included the correct functional form, and whether there is heteroscedasticity in the model. Here we should like to do the same thing for the case where we have a broader class of models, which is the generalized linear model. So to begin with, we will first introduce the definition of a residual. You will see that although it is quite natural to define a residual as the fitted minus observed for a linear model, the comparative definition for a generalized linear model is not actually so straightforward. So we have alternative classes of residuals, so for example the deviance residual, the Anscombe residual, and so on. And the correct choice will often depend upon the purpose of our analysis. So we shall define the residual, look at the motivation, see their illustration, and do some fitting using R. Residual analysis for a GLM. First, let us explore what is the concept of a residual. You have already seen the term residual in the context of linear models. So, for a linear model, we have a data point, a corresponding fitted value which we obtain using, say, the technique of least squares, and the difference between these, the observed and the fitted, is our definition of a residual. So, in terminology, y is our observed data point, mu hat, say, is the fitted value, and by definition, the residual is y minus mu hat. We have seen how to use residuals before for linear models. There are many ways in which we can use them. So once we obtain the fitted values, which you know is given by x beta hat for a linear model, we compute the residuals as y hat minus x beta hat, and we use them in various ways. So one would be to plot y minus y hat against y hat itself, and you know that the result should be a plot which is completely random and uncorrelated. We could also plot the residuals, which are commonly denoted by E hat, against the covariates, and in this case we get some idea about the adequacy of the functional form, as also we can look at the spread of the residuals and get some idea of heteroscedasticity. It turns out that when we perform residual analysis for a GLM, it is not quite so straightforward. So say for example y was binary, you know that we are not really fitting a model to y itself, but to the logit of the expectation of y. So if we were to do expected minus observed, because many of the y's are clustered at zeros and ones, the residuals would also be clustered. So we have several different concepts of residuals for a GLM. The first is the Pearsonian residual. So Pearsonian, you know, refers to the Pearsonian chi-square, and it is a summary measure of observed minus fitted. Similarly, the Pearsonian residual has for its numerator y minus mu hat, which is observed minus fitted. Now, if we were to stop there, there would be a problem, because we know that when we fit a GLM, the y's are by definition heteroscedastic. So we have a variance function v mu, which relates the variance of y to mu, and to be able to use the residuals for any kind of analysis, we need to standardize the differences y minus mu. So the Pearsonian residual is the standardized difference given by Rp equal to y minus mu by square root over v mu, where v mu is the variance function. Of course, we do not know the true value of mu, and to calculate the Pearsonian residual, we would substitute mu by mu hat. The motivation for the Pearsonian residual comes from the fact that summation of Rp square is our familiar chi-square measure of goodness of fit. So this is the first and common measure of a residual for a GLM. However, a problem with this is that the distribution is often skewed in the case when y is non-normal. As a result, the residual does not have the properties for normal residuals, and as such, the use of these residuals can lead to results which are difficult to interpret. Let us next come to another residual, which is the Anscombe residual. So the motivation for the Anscombe residual comes from the result which I mentioned on the earlier slide, which is that the Pearsonian results can be skewed and hence non-normal. The motivation for the Anscombe residual, which comes from Wedderburn in some unpublished work and is also mentioned by Barndorf and Nielsen in their 1978 paper, comes from the fact that when we calculate observed minus residual, we do not really need to do it on the scale of y, but we could do it on the scale of a function a of y. So Wedderburn shows that in order to get normality, in the case where we are using an exponential family, the optimum choice of a is given by a is equal to integral d mu by variance function to the power of 1/3. So thus, for the Poisson distribution, it is possible to show that since the variance function is given by v mu equal to mu, the function a is given by integral of d mu by mu to the power 1/3, which is equal to 3/2 mu to the power 2/3. So because we should standardize the residuals, we can calculate the variance of the corresponding function using the delta method, and thus for the Poisson distribution, the Anscombe residual is given by Ra equal to 3/2 y to the power 2/3 minus mu to the power 2/3 divided by mu to the power 1/6. A third and more common residual for the GLM, in fact, the most common form of the residual for the GLM is the deviance residual. The motivation for the deviance residual is similar to the Pearsonian residual as well as in some sense to the Anscombe residual. It is defined as Rd equal to the sine of y minus mu into square root of di. Di here is the contribution of the ith individual to the overall deviance. So, the deviance, capital D, can be written as summation of di, where di denotes the contribution from the ith term. The corresponding residual for the ith individual is then square root of di multiplied by the sine of y minus mu. So when we say sine of y minus mu, we mean a function which takes the value +1 or -1 according as y is greater than or less than mu. Of course, again, we do not know the true value of mu, and in this case, we would substitute mu by mu hat. For the Poisson distribution, we know the form of the log likelihood and hence the form of the deviance, and using this, the deviance residual turns out to be Rd equal to sine of y minus mu into twice y log of y by mu minus y plus mu whole to the power half. Again, we substitute mu by mu hat to get a form which is usable. We need to compare between these residuals, and in our comparison, it is possible to see that The Anscombe and the deviance residuals, although they come from quite different motivations, are often quite similar in practice. So to see this, for example, for the Poisson distribution, note that the Anscombe residual for the Poisson distribution is given by Ra equal to 3 by 2 mu to the power half into c to the power 2/3 minus 1. We substitute y equal to c mu. For the Poisson distribution, the deviance residual is given by Rd equal to sine of c minus 1 mu to the power half into 2 c log c minus c plus 1 whole to the power half. If we perform a Taylor series expansion of the second term, it is possible to show, and in fact has been showed by McCulloch and Nelder in their book on generalized linear models, that the values of the Anscombe residual and the values of the deviance residual are often identical or very similar. The values of the Pearsonian residuals for the Poisson family can be somewhat different. Another commonly used regression model in the class of GLMs is logistic regression. Here are the forms of the residuals for logistic regression. So if pi I hat denotes the fitted probability, the Pearsonian residual is given by Ri equal to yi minus pi I hat divided by the square root of pi I hat into 1 minus pi I hat. I am assuming here that yi refers to ungrouped binomial data, that is, we have a Bernoulli family which takes the value 0 or 1. In this case, the log likelihood is given by L equal to summation over I yi log pi I hat plus 1 minus yi into log 1 minus pi I hat, and hence the deviance residual is given by di equal to si into root over minus 2 yi log pi I hat plus 1 minus yi into log 1 minus pi I hat, where si is equal to 1 if yi equal to 1 and si equal to minus 1 if yi is equal to 0. We may next wish to perform some overall summary measures of goodness of fit, and we can do this using goodness of fit tests. So we know that the Pearsonian goodness of fit test will hold for many families of categorical data, and similarly we have also defined the concept of a deviance function before and seen how the deviance can be used to measure goodness of fit. After performing residual analysis, we might also wish to perform a goodness of fit test. So you have heard before of the Pearsonian goodness of fit test, which holds for categorical data, and we have also introduced the deviance function and seen how the deviance function can be used to test goodness of fit. So one summary test which is available to us is to use chi-squared tests based on the sum of squared Pearsonian or deviance residuals. However, this test does not often work well in practice, and there are extensive comparisons on this which have been shown by Hosmer in his 1997 book. A better test has been proposed by Hosmer and Lemschau, and to implement this you can use the Hoslem.test function in the resource selection library in R. Next, let us move on to the concept of the hat matrix. You are already familiar with the concept of a hat matrix for linear models and have seen that this is given by x into x prime x inverse x prime, where x denotes the deviance matrix, where x denotes the design matrix. The hat matrix for GLMs is given by H equal to w to the power half x, x prime wx inverse, x prime w to the power half, where w is the inverse variance or the weight. Now the hat matrix for GLMs is somewhat different from the hat matrix for LMs. So to begin with, Note that if we were to have binomial data, for example, then pi hat is not obtained by multiplying y by the hat matrix. Now note that it is not possible for any matrix to multiply y and lead to y hat, because in this case it would not be possible to have pi hat restricted within the range of 0 and 1. However, there are some properties which the matrix H given on this slide shares with the hat matrix of linear models. So firstly note that H of R is equal to 0, where R is the vector of Pearsonian residuals. If you compute H transpose, then you will see that H is equal to H transpose, that is, H is symmetric. Also, if you multiply H into H equal to H square, you will see that H square is equal to H and that H is idempotent. Also, H w to the power half x is equal to w to the power half x, and x prime w to the power half h is equal to x prime w to the power half. If you replace w by the identity matrix, then you will see that a similar property holds for the hat matrix from linear model. We next look at the concept of standardized residual. So the standardized Pearsonian residual and the standardized deviance residual can be obtained as RSI equal to Ri into divided by square root over 1 minus HII, and the standardized deviance residual is given by DSI equal to Di by square root over 1 minus HII. HII, of course, here is the ith diagonal element of the hat matrix which we saw on the previous slide. It is often preferable to use standardized residuals rather than the unstandardized version, and the reason is that the standardized residuals tend to show greater symmetry. We have also defined the concept of leave one out residuals for linear models. Leave one out residuals are used to study influence. By influence we mean the effect which the observation yi has on the corresponding fitted value yi hat. So an observation would be considered influential if dropping yi from the model would lead to a yi hat which was very different to the yi hat obtained if we include y in the model. Leave one out residuals are used to study influence. However, although they are conceptually based on the idea of dropping an observation and looking at the effect it has on the fit, in practice, at least for linear models, due to the presence of certain matrix identities, it is not really necessary to drop each observation in turn and to refit the model n times, where n denotes the sample size. The matrix identities hold approximately for GLN. So although we cannot explicitly compute the leave one out residuals, we can calculate reasonably well-behaved approximations for GLNs. So in general, there are two classes of residuals. The deletion residuals, you may be familiar with terms such as df betas and Cook's distance for linear models. It is also possible to calculate them for GLNs. And the idea here is, as I said, to drop an observation yi and to look at the effect it has on the corresponding fitted value pi I hat or lambda I hat, as the case may be. There is also another concept which looks at infinitesimal perturbation. So the idea is to look at very small perturbations in the model and to see the effect of this perturbation on the corresponding fitted values. Finally, let us look at an example in R which illustrates residual analysis. Our data set here is the survival of trout eggs depending on time and location. So boxes of trout eggs were buried at 5 different stream locations and retrieved at 4 different times. The number of surviving eggs was recorded and is recorded in the dataset trout eggs as the variable survive. The dataset is a data frame with 20 observations on 4 variables. So the first variable is the outcome survive, total is the number of eggs in the box, location is the location in the stream, and period is the number of weeks after placement. So both location and period are factor variables. For more, you can look at the library far away and the trout eggs data set, or the reference to Manley given at the bottom of this slide. To perform residual analysis in R, we first use the GLM function to fit a logistic model of survive on location plus period. So here we have used the GLM function on cbind survive and total minus survive, that is the number of successes and the number of failures, and regress this on location plus period. I have stored this in the R object bmod. So note the family is binomial, which by default will fit a logistic regression. When I call bmod, I can see the coefficients and the deviance. To look at the residuals, I use the residuals function. So residuals of bmod will call the residuals, in this case by default the deviance residuals, and I can do a half normal plot of this to illustrate their use. On this slide we see 2 plots. The plot on the left panel is the half normal plot of the residuals. The plot on the right is a plot of the empirical logits and is obtained using the chunk of code given on the bottom of this slide. So looking at the half normal plot and the empirical plot, we see that although the summary deviance is rather large, there really is no strong indication of outliers or influential values. Another reason why we could have a large value of deviance, even though we do not have outliers, is heteroscedasticity, and thus, having ruled out the presence of influential values, we can next explore how to deal with overdispersion, which appears to be present in this example. So to do this, we shall calculate an empirical estimate of the dispersion scale parameter, and here we have obtained it as sigma 2, which is the sum of residuals, in this case Pearsonian residuals, divided by the sample size. We can see here that the scale factor is 5.33, which is rather larger than the normal scale factor, which is taken to be 1 for the binomial family, and thus it appears to indicate that we have substantial overdispersion in the model. We can next recompute our estimates and standard errors, assuming that the scale parameter is given by sigma 2, and you can compare this to the previous set of estimates and see that although the estimates will not change, the standard errors will be adjusted, and hence the z values and the probabilities will change. It is a good exercise for you to compare this to the unadjusted output given on the previous slide. In this module, we have defined the residual for the GLM. We have seen that although the definition of a residual is quite natural in linear models, in GLMs there are different considerations which lead to different categories of residuals. So to begin with, we have the Pearsonian residual and we also have the deviance residual. Both of these are based on the contribution of an individual to summary goodness of fit measures, in this case the Pearsonian chi-square and the deviance chi-square. It has been shown that the Pearsonian residual can tend to be skewed and hence behave in a non-normal fashion. So based on this motivation, Anscombe defined a different class of residuals, which is to approximate the behavior of the residual to normality as quickly as possible. So we have yet another class of residuals called the Anscombe residual. So although this might sound confusing in practice, it is possible to show that the Anscombe and the deviance residual in many cases will tend to give similar results. Having defined the different residuals, we have also considered the goodness of fit tests and seen that the Pearsonian and the deviance residuals, although they lead to goodness of fit tests, do not always behave in an optimal fashion. This has been studied by Hosmer and Lemschau, and they have also proposed an alternative test. We have defined a hat matrix for GLMs. We have seen before that the hat matrix is extremely useful for the linear model, and it can be used to map the observation vector y into the vector of fitted values. So although this property does not hold for GLMs, and in fact, if you think for a moment, it is not possible for such a linear mapping to happen for GLMs for any matrix, because in that case it would not be possible to preserve the restricted ranges. We have defined a hat matrix in an analogous manner and seen that it shares many of the properties of the hat matrix, which is used by the linear models. We have thus been led to the concept of standardized residuals, where we standardize by the square root of 1 minus HII, HII being the il diagonal element of the hat matrix. We have next defined the concept of leave one out residuals. Leave one out residuals are easy to compute in practice for linear models because of the presence of certain matrix identities based on partition matrix. It is not necessarily to do any recomputing after dropping an individual observation. However, for GLMs, we do not have these matrix identities, but we can use certain approximations based on the IRLS equations to get approximate leave one out residuals. In the case of GLMs, we do not have any such matrix identities. However, it is possible to use the IRLS equations to get some approximations for the leave one out residuals. And these residuals can be used in two ways. One, as deletion residuals, like the traditional DF betas and the Cook's distance, which you have seen for linear models. The other, as infinitesimal perturbations of the model. Finally, we have seen how to extract the residuals from a GLM object and how to use them to explore influence, goodness of fit, and overdispersion.